Hey guys, how are you today? Welcome to your third week of the Chemistry Survivors course. I know this may be strange for some of you because this is the first time that you hear my voice in one of your PPTs. My name is Sofia Berny. I'm one of your teachers along Alondra Berenice. Today we are going to be giving you the class of Stoichiometry, and this is all about you learning to calculate the amount of product from the amount of separate reactants in a chemical equation. It is pretty simple topic. You will learn it easily. I have for you some tips, and we are going to start the class. So, what is stoichiometry? Stoichiometry is the calculation of the quantities of chemical elements or compounds involved in chemical reactions. You can calculate with stoichiometry how much product comes from the reactants or how much reactant comes from the product. The mole is a unit that counts particles such as atoms, molecules, and ions. A mole contains 6.02 times 10 to the 23rd of those particles. This large number is called the Avogadro's number. The Avogadro's number is named like this because of the Italian physicist Amedeo Avogadro. Remember this number, please. It's very important for the next slides that we are going to be reviewing. And as an extra comment, I want to say that 1 mole of an element contains 6.02 times 10 to the 23rd atoms of that element, such as 1 mole of a compound contains also 6.02 times 10 to the 23rd molecules of that compound, and so on. The Avogadro's number as a conversion factor. We can convert moles of a substance into the number of particles in the substance, using the Avogadro's number as a conversion factor. You may remember from your classes from math or physics how to do this type of conversion. It is very easy, and it will be explained also in here. We are going to do this work example. Imagine you have 4 moles of iron atoms, and you want to know how many particles are in there. So you are going to use the conversion factor of Avogadro's number because, remember guys, that for every mole that there are also 6.02 times 10 to the 23rd particles of that kind of substance. So we are going to do this. As we have that the relationship is, for every mole of iron atoms, we have the Avogadro's number of iron atoms. So we are going to multiply the number of moles that we have, in this case 4, times the Avogadro's number in order to know how many atoms of iron are there in 4 moles of iron. So we do this calculation, and the answer will be 2.41 times 10 to the 24th iron atoms. Moles of elements in a formula. You can use the subscripts in the empirical formulas of compound to infer how many particles of each element are there in a mole of the compound. You have to do this relationship between the atoms and the moles from the empirical formula, just as in this example, that is aspirin, whose empirical formula is in the table, specifically in the green part. It is C9H8O4, and as you see in the empirical formula, you have 9 atoms of carbon, 8 atoms of hydrogen, and 4 atoms of oxygen, meaning that in 1 mole of aspirin, you will have 9 moles of carbon, 8 moles of hydrogen, and 4 moles of oxygen, and you are conserving the proportion that it was at first in the empirical formula. Finally, by using the conversion factor in the previous slide, you can calculate how many particles of each element are there in 1 mole of the compound. I recommend you to do this as a practice, but it is not necessary and it will not be graded as part of the molar mass. This term refers to the number of grams that equals the atomic mass of that element, meaning that 6.02 times 10 to the 23rd atom of carbon is exactly the same as 1 mole of carbon. That is exactly the same of 12.01 grams of carbon, which is the atomic mass of carbon that you can find in any periodic table. Calculations using molar mass. In the same way that you use Avogadro's number to convert the moles of a substance into the particles of a substance, you can use the molar mass to convert the moles of a substance into the grams of the substance. For example, it is shown in your PPT, 1 mole of magnesium is equal to 24.3 grams of magnesium. This number was obtained from the periodic table in your book, and the conversion factor in this case, we are going to find how many grams of magnesium are there in 3 moles of magnesium. So, you just have to multiply 3, because that's the moles of magnesium, times 24.3 grams, because that's the atomic mass, molar mass of the magnesium, and if you do it in your calculator, it must give you the answer that is 72.9 grams of magnesium. See, it was exactly the same process that we use in the Avogadro's number. Factor conversion. Mole relationships in chemical equations. First of all, there is conservation of mass, that it is also known as the law of conservation of the mass, that we've seen throughout all the chemical equations section of this course, and you might heard of it in previous courses, and it states that there is no change in the total mass of the substances reacting in a balanced chemical reaction. Then, this is obviously as a pinpoint that I must remember, and then there is the new content that are the mole-mole factors. And they are made from a chemical equations and are used to convert moles of a substance into moles of another substance. Just as the equation shown below, that you have already balanced it. Remember, it is important to balance these equations because then you won't have the mole-mole factor correctly. And as you can see, the mole-mole factor is just the relationship between two reactants, two products, a reactant or a product in a chemical equation. For example, for every 2 oxygen molecules there will be 2 carbon dioxide molecules. Mole-mole factors in calculations. Mole-mole factors are used in conversions, as well as you've seen in the past examples with the molar mass and the Avogadro's number. In this case, you are seeing in your screen a balanced equation between aluminium and oxygen molecule that produces aluminium oxide. In this equation, you can see that the relationship between aluminium and oxygen molecule is 4:3. And if you have 12 moles of aluminium, you'll have to use the conversion factor. There will be 3 moles of oxygen molecules for every 4 moles of aluminum atoms. So you will have the next operations. 12 moles of aluminum will be divided by 4 moles of aluminum. That will give you 3 moles of aluminum. That will be multiplied by 3 moles of oxygen. That ends with 9 moles of oxygen molecules in total. What we did now is the same conversion, but as you've seen, it is just a rule of 3. Mass calculation for reactions. From the mass in grams, you can calculate the number of moles by using mole-mole factors. You can see the number of moles. Then the molar mass of the substance is used to convert moles to grams. This is the biggest conversion that we've seen until now, and it is pretty easy. It's the same process, and I will walk you through it. So, let's say that you have 54.6 grams of this hydrocarbon, and just that. We want to convert it to CO2. Let's imagine that the mole-mole factor between this hydrocarbon and CO2 is 2 to 4, meaning that for every 2 moles of the hydrocarbon, you will have 4 moles of the carbon dioxide. So, we have 54.6 grams of the hydrocarbon, and this hydrocarbon has a molar mass of 26 grams, meaning that we will have to divide 54.6 grams of hydrocarbon by 26 grams of the hydrocarbon, and the answer will be divided by the 2 moles of the hydrocarbon times the 4 moles of the carbon dioxide, and the answer of this second part will be divided by 1 mole of CO2 and multiplied by the molar mass of CO2, which is 44, and the answer is 184 grams of carbon dioxide. Percent yield and limiting reactants. Well, until this point we have assumed that all of the reactants were completely changed into product. This is an ideal situation. We were assuming that the 100% of the reactants were converted into products. In reality, this doesn't happen. In the lab, we always have a residue where we have a small amount of the reactant, of one of the reactants left. And well, this creates a percentage yield, and we have to calculate it by the formula. Percentage yield is equal to the actual yield over the theoretical yield times 100%, just like you will calculate any percentage. It is obvious in this formula that the actual yield is how many of the actual product is obtained from the reaction, and the theoretical yield is how much was we supposed to obtain from the reaction. Limiting reactants. A limiting reactant is the reactant that is used up first. As I've said in the previous slide, you will have some of the reactant left unchanged. So that is the excess reactant, and the reactant that you cannot see again is the limiting reactant because it was finished, it was used up first. There are 2 pretty simple concepts, but we are going to reinforce them through the next slides. calculating moles of product from a limiting reactant. You have to see which is the limiting reactant, and you will see the residue on the bottom of your beaker, but maybe you won't know which reactant it was because it may be so little that you cannot distinguish. So we can do this in a theoretical way, and I'm going to show you how. First, you have to create mole-mole conversion factors, as we've seen in the last slides. And imagine you have hydrogen molecule and chlorine molecule, and that's formed chlorhydric acid, as we all know. Now, suppose that in the mixture where this reaction is occurring, there were only 2 moles of hydrogen and 5 moles of chlorine. So we have our mole-mole conversion factors that are between the reactant and the product. The first one will be the hydrogen one. We have 2 moles of hydrogen. The mole-mole factor is for every mole of hydrogen, you have 2 moles of the acid, and this gives us a total amount of 4 moles of chlorhydric acid. And for the next, we have 5 moles of chlorine, and also the conversion factor here is 1 to 2, meaning that there's the double, and we have 10 moles of the acid. So, as the 4 moles is less than the 10 moles, we have to say that the hydrogen is the limiting reactant because it will be used up first during the first 4 moles, then the chlorine that it can be used up to 10. Calculating mass of product from a limiting reactant. Well, your quantities are not always given in mole, especially when you are in a lab practice. You are going to have grams instead of moles, but you can also calculate the mass of the product that you will have by using the limiting reactant. And let's do this in a worked up way because it may be a difficult concept to grab your mind, so we are going to do this together. Imagine that you have this silicon oxide and carbon that are going to react and form silicon carbide and carbon monoxide. And let's suppose that we only have 70 grams of the silicon oxide and 50 grams of the carbon. So how many grams of CO2 are there produced? Well, we are going to have to write these mole factors as we've seen. For every silicon oxide, there will be 2 carbon monoxides. For every 3 carbons, we are going to have 2 carbon oxides. And as for the molar mass factors, a mole of silicon oxide is 60.1 grams. A mole of carbon, as you know, is 12.01 grams. For making this problem easier, we are just going to say that it's 12 grams. And well, that is it for the mole factors and the molar mass factors that are needed there. So we are going to calculate the number of moles of the product from each reactant and determine the limiting factor. Please click on the next slide so you can see this process. So we have the 70 grams of silicon oxide, meaning that we are going to divide it over the molar mass that, as I said before, is 60.01 grams. And we are going to multiply that times the 2 moles of carbon monoxide because that was the mole factor, and it gives us 2.32 moles of carbon monoxide. We are going to do the same with the carbon. We have 50 grams of carbon. We are going to divide this over 12 because that's the molar mass of carbon, and then we are going to multiply it times 2. No, we are going to divide it times 3 and multiply it times 2 because we are respecting our mole factor, okay? And this must give us 2.77 moles of carbon monoxide. Are we on the same track? Well, if you cannot, we can always repeat this process with your calculator, but if you are, you must have noticed that 2.32 is less than 2.77, meaning that the silicon oxide is our limiting factor here. So, as we only have amount to produce a maximum of 2.32 moles of carbon dioxide, this is the number of moles that we are going to use in the conversion of the grams of CO2 that we can have. So there is 2.32 moles of carbon monoxide, my mistake. And we are going to divide this over 1 mole of carbon monoxide and multiply it by the molar mass, that is 28, and it gives us a total amount of 65 grams of carbon monoxide. Just as a summary, we've seen that we can convert grams to moles, moles to particles, atoms in a particle, and particles to moles, moles to grams. It is very easy. We always use conversion factors, and the conversion factor for grams to mole is the moles over the molar mass, and for moles to grams is the molar mass, and for moles to particles is the Avogadro's number over 1 mole, and for particles to moles is 1 mole over the Avogadro's number, and so on. You can see it in the image that I'm sharing with you. Pretty easy, it's the same concept. You mustn't have any problems by now, but if you do, I'm including, as always, a further knowledge section. So this is a further knowledge section. Including today this video from Crash Course. It is a simple way to review all these things that we have learned, and it is also another way to explain it. It is pretty easy. It may clear up your mind about some of the concepts that we've seen today. It is also including some other pinpoints so you can have a better idea, or you can have a new way of seeing this topic. I don't know, watch it, it's pretty good. It explains the same that I've explained, but in another way. He's also very charismatic. You will understand him. He's very visual. Hope that you can understand him in another way or complete any of your doubts. So these are the reference, pretty standard way to show you. The Crash Course link for the video is included in case any of you have trouble viewing it directly from the PPT. And then there is the book that I used to further our knowledge or definitions that I'm showing here in this PPT. It is the book that you have in your reference section, and you can also view the same content in there. So this is everything, guys. If you have any doubts, you can ask Teacher Berry or me about the content of the class. Our contact information is under Leader Information section. And this is all for this week. Have a good weekend, guys. Bye-bye.